Hi. I went away there for a second, but I'm back. Okay, so last time we talked about that there is, we've boiled the problem down to now showing that the determinant is defined, functions satisfying the four properties exist, provided that we can show that the determinant of permutation matrices is well defined. Many instructors will leave it there and move on to other material. If you want to see that full development, then we're going to cover it here on this slide, on this video. But because it's optional for many instructors, we're not going to do the check-in. We're just going to proceed along with the material, just so that a person who skips it doesn't miss the check-in. Okay, so we're showing that determinants exist, and what remains to show is that the determinant of a permutation matrix is well defined. In order to show that the determinant of a permutation matrix is well defined, what we've got to do is come up with a way to calculate it. And so here's the way to calculate it. If you give me a permutation where k is bigger than j, then we say that they are in an inversion of their natural order. And similarly, in a permutation matrix where iota k comes before iota j, we say that the two rows are in an inversion of their natural order. So an example tries to make a little clearer what's happening here. So if you have 3, 2, 1, the 3 comes before the 2. That's in an inversion of the natural order of numbers. The 2 comes before the 1. That's in an inversion of the natural order of numbers. And the 3 comes before the 1. That's in the inversion of their natural order. I have a little table here that helps a person keep track of who's before who. The 2 comes before the 1, the 3 comes before the 1, and the 3 comes before the 2. So I count 3. 1, 2, 3, 3 inversions of natural order there. So I am trying to figure out somehow a way to find the determinant of a permutation matrix, and I'm going to compute the determinant of a permutation matrix by assigning some number to it, and that number is going to have to do with the number of inversions, basically the number of row swaps it takes you to get back to the identity. Here's another example. So I have a permutation matrix. In each row is a single one in each row and each column. I said that backwards. So there's a 1 in each row and each column. Everybody else is zeros. That's iota 2 because the second entry is the 1. That's iota 1. That's iota 4. That's iota 3. So looking there at the 2, 1, 4, 3, we can see that 2 comes before 1. 3 and 1 are good. 3 and 2 are good. 4 and 1 are good. 4 and 2 are good, and by 4 and 2 are good, I mean that it's not the case that 4 comes before 2, instead it's the opposite, but 4 comes before 3. So I count a total, this is my little bookkeeping device, I count a total of 2 inversions. And of course, I'm interested in calculating the determinant of a permutation matrix, so I'm interested in how many row swaps, an odd number or an even number of row swaps, does it take to get from the permutation matrix you're given to the identity matrix. Because remember, each row swap changes the sign, the SIGN of the determinant. So this lemma says a row swap in a permutation matrix changes the number of inversions from even to odd or from odd to even. If you do a single row swap, swap 2 rows, any of them, row 5 and row 23. That will change the number of inversions from even to odd or odd to even. That is, it flips the parity of the number of inversions. The book contains a proof, as happens so often. I consider these videos to be a kind of run-up to the book. You would look at the videos first, and then you would try to follow along in the book. So I'm going to do an illustrative example, and that way when a person comes up to the book, they say, oh yes, I remember that part. So here we go. There are 2 cases. The 2 cases are that the rows are adjacent, and the second case is that they aren't adjacent. So here's what happens when you swap adjacent rows. Row 2 and row 3 here. I'm going to swap them, and you see that I've swapped row 2 and row 3. I'm going to count the number of inversions. So here is what happened, and here's what happened. So it used to be the case that, that I had iota 1 and then iota 3. But we swapped these 2 rows, and now I have iota 3 coming before iota 1. And we see that here. It used to be the case that 1 and 3 were in their sort of natural relationship. Now it's the case that 3 comes before 1. So we added exactly one inversion. These other x's, and for that matter the non-x's, things that are not this box here, are unaffected by the changing of by the swapping of these two rows. The only thing that's affected is that it used to be the case that 1 came before 3, so it don't get an x. Now it's the case that iota 3 comes before iota 1, so it does get an x. Okay, so that's for adjacent rows. What happens when you swap non-adjacent rows? Okay, so what happens, for example, if you take these two permutation matrices and you swap row 1 with row 4? See up here, row 1 was iota 4, and now I swapped it, so down it goes to the bottom. Here, row 4 was iota 3. I swapped, so it goes up here to the top. Well, to swap these non-adjacent rows, I'm just going to do a sequence of swaps of adjacent rows. So to get row 1 down to row 4, I'm going to swap row 1 and row 2, and then I'll swap row 2 and row 3, and then I'll swap row 3 and row 4. And now, after those steps, what used to be row 1 is all the way down to the bottom of the matrix. Now, the bottom has not come up to the top yet. I'll get to that. But what was at the top has gone down to the bottom. Okay, so let's take the iota 2 that used to be at the bottom and move it up. So you swap row 3 and row 2, you swap row 2 and row 1, and you're moving iota, oops, here it is. You're moving iota 2 all the way up to the top. That was 1, 2, 3, 4, 5 row swaps. So even non-adjacent rows will take an odd number of swaps, each of which flips the parity of the number of inversions. That is, I took 5 swaps. We know that each swap flips the parity. So the total number of flips of the parity is, right, in total the parity switches because there's an odd number of swaps. So whatever the parity was, maybe it's even, switches to odd after an odd number of swaps, or if it was odd, it switches to even after an odd number of swaps. So the way I'm going to find the determinant of a permutation matrix is I define this function, the sinum. Sinum of a permutation is -1 if the number of inversions is odd, and it's +1 if the number of inversions is even. So that is to say, I want to give here a formula for calculating the determinant of a permutation matrix, and I'm going to calculate the determinant of a permutation matrix not by doing Gauss's method or something. Instead, I'm going to count the number of inversions. The number of inversions is related to the number of swaps, and then I'll be done. So just as an example, here's the permutation 3, 2, 1. There's the associated permutation matrix. There's obviously an odd number of inversions. 3 comes before 2, 2 comes before 1, 3 comes before 1. And so the sinum is -1. The permutation 3, 2, 4, 1 has 4 inversions. So the sinum is +1. So you take the number of inversions. If the number of inversions is even, you write down a +1 for the outcome of this function. If the number of inversions is odd, you write down a -1 for the outcome of this function. Obviously, given a permutation matrix, you can count the number of inversions. Look, I just did it. So given a permutation matrix, you can count the number of inversions. And so you can decide +1 or -1. There's no question about whether that's defined. And that's what I'm looking for. I'm looking for a no question about whether that's defined. You can't do this two different ways. Definition of the determinant of a permutation matrix. So if a permutation matrix has an odd number of inversions, then swapping it to the identity matrix takes an odd number of swaps. If a permutation matrix has an even number of inversions, then swapping it to the identity matrix takes an even number of swaps. In other words, we can find the determinant of a permutation matrix by counting the number of inversions. We don't have to do those swaps. We can count the number of inversions. And you can say, well, I don't think that's nearly as clear. I don't care. All I care is that you can only count the number of inversions in one way. But you can swap the permutation matrix to the identity in more than one way. So it's not clear that you have well-definedness of plus or minus, but it is clear that you have well-definedness of number of inversions. That part's clear. So this represents the goal. This is the thing we've been working for. and it's actually straightforward, but often corollaries are you got to the end of all the work, and so the work is all done here. The identity matrix has 0 inversions. To change an odd number to 0 requires an odd number of swaps, and to change an even number to 0 requires an even number of swaps. That's okay. So very straightforward. So, we'll be, have a little celebration JavaScript animation here. So we're trying to show that a function exists that satisfies the 4 conditions in the definition of determinants. We have to show that for each input square matrix, there is a well-defined output value. That Gauss's method can be done in more than one way, so it isn't obvious that by keeping track of the signs and by multiplying them down the diagonal, we always get the same output. That if I do it one way and you do it the other way, we'll guarantee to get the same number. So instead, what we did was we produced the permutation expansion, and that left us with reducing the entire problem to finding the determinant of a permutation matrix. But the corollary that we just saw says that the determinant of a permutation matrix is the signum of the permutation. The determinant of a permutation matrix is the signum of the permutation. So I replaced that in the formula, and now, after a lot of work, we've got that desired formula for a determinant. So the advantage of this formula is that the number of inversions is clearly well defined. You can count them, like I've done a couple examples of counting them already. So we'll be done if we show that D satisfies the conditions in the definition of determinant. Okay, so a lot of work, finally getting to sort of success here. So the lemma says that the function D is a determinant, and therefore determinant functions exist. So we show that determinant functions exist by producing a formula for the determinant. Again, said many times, but say it one more time. In practice, to calculate a determinant, if you have a homework problem that gives you a 4x4 matrix, to calculate a determinant, we won't calculate it this way. This way is very slow. I mean, maybe there'll be an exercise that says use the formula to calculate the determinant, but typically in practice, you will use Gauss's method to calculate a determinant. But the existence of the function guarantees that there is the existence of the formula guarantees that there is a determinant function. That's what we needed. Okay, so the book has the proof which verifies the definition of determinants for conditions. Instead, I'm going to go through an illustrative example, and when you see the example's pretty involved. You'll see why we're not going through the details of the proof. Not that they're embarrassing, but just that you got to start with numbers before you go to letters. Okay, so here's the D expansion. Remember this, did you notice? I'm not calling this DET, I'm calling it D because we haven't yet established that it's DET. Okay, so this is the D expansion for a 3x3 matrix, and doesn't it look just exactly like the permutation expansion? Of course it does. I don't have room on the slide, I'm sorry, it just took too much space on the slide. So instead of using SGN, I wrote S. S, 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 and S. I'm sorry, it's just a question of real estate, that's all. Okay, and I'm going to illustrate the proof's verification of the 4 condition by using the 1, 2, 3, 4, 5, 6, 7, 8, 9 matrix, just because I'm not a very creative person. Okay, so condition 4, that the determinant of an identity matrix is 1, is you go back and look here and you say, well, in the determinant matrix, A, F, and J are 1, everything else is 0. So if you have anything other than A, F, and J, you're multiplying by 0. Anything other than A, F, and J, anything other than A, F, and J, anything other than A, F, and J, anything other than just A, F, and J, you're multiplying by 0. So you're just left with this, and so you get 1. Okay, and the other conditions are verified in much the same way. I'm going to go back to that formula and check that the cases work. Some of them are more detailed, of course more involved, but the basic idea is I go through the conditions and say, does condition 1 hold, does condition 2 hold, does condition 3 hold, that kind of stuff. Condition 3, so I'm going to multiply a row by k. Okay, so I chose here to multiply the second row by k. When you go back to that formula 2 slides ago, I won't go back every time, but maybe I'll go back this once. When you go back to this formula here, Here's the expansion. There's a 5K, a 6K, a 4K, a 6K, a 4K, and a 5K. Every one of these terms has one single K in it. None of them have 0, none of them have 2. Every one of these terms has 1K. Factor out the K. The result is K times this big, as it was 2 slides ago. Okay, condition 2. So condition 2 talks about row swap changing the sign of the determinant. So we have to check that, for example, if you swap row 2 and row 3, that the determinant will have its sign changed. So we're going to check that if you swap rows 2 and row 3, then the D function has its sign changed for this one matrix. And of course, I'm going to try to do it in a way that suggests how the proof goes. Okay, so here we go. I'm expanding. This is the expansion up here. This is the expansion of the left-hand side. The D expansion of the left-hand side. This is the D expansion of the right-hand side. And of course they're different because they have different things in the second entry and that sort of stuff. But they match up in some way. Do you see that the 159 matches up with the 195? Do you see that the 168 matches up with the 186? And the 249 matches up with the 294? And the 267 matches up with the 276, like that. Okay, all right, so a person sees that. So the two match term by term. For example, the two 159s match up. Let's check again the two 159s. Okay, 159 and 195, obviously not an important difference. And now let's look, what does the signum say and what does the signum say? Well, in swapping row 2 and row 3, I went from a 111 there to a there. So in swapping row 2 and row 3, I went from an identity matrix that has 0 many inversions to a permutation matrix that has 1 inversion. 168. I have there a permutation matrix that a single row swap would take it back to the identity. Down here, 186, I have a permutation matrix that takes 0 many row swaps to go to the identity. So again, the difference is 1 swap. So the SIGN of this term is different from the SIGN of this term. One's plus and one's minus. And likewise here, the SIGN of this term is different from the SIGN of this term. One's minus and one's plus. One more, you get the idea, but one more. Okay, so 249 matches with 294. What's the difference? Well, let's see. How many row swaps does it take to make this the identity? I think a single row swap will make this the identity. How many row swaps does it take to make this the identity? I think you have to swap 1 and 3, and then I think you have to swap 2 and 3. So this will have this will take 1 row swap to get to 0, to the identity. This takes 2 row swaps to get to the identity. So the sign of this and the sign of this are opposite. Every one of these terms has the opposite sign from the associated term below. Again, the 159 has the opposite sign, the S part, has the opposite sign from the S part of the 195. The 168 has the opposite sign, the S part has the opposite sign from the 186. The 249 has the opposite sign, the S part has the opposite sign from the 294, and like that. So this and this are negative, term by term, negative. Okay, last condition, the row combination condition, and this is the most involved one. It's a little on the tricky side. I don't want to say tricky, a little big. It takes a lot of real estate. Okay, so I used the numbers 1 through 9 already, so I took 10 times row 1 plus row 2. And I'm going to compare left and right. I'm going to take the D expansion left and right. So here's the D expansion on the left. And of course, I didn't all fit on one slide, so the D expansion on the right is on the next slide. What do I mean by the D expansion on the left? Why, first I took, this term, this term, this term, sort of this term, this term, this term kind of stuff. So here we go. The second matrix has this D expansion. If you break along the plus signs, then you get two sums. You get the 159. There we go. I'm breaking along this plus sign, that plus sign, that plus sign, that plus sign, etc. You see the 159, there'll also be a 129. You see the 168, there'll also be a 138. You see the 249, and there'll be a 210-9, like that. And here they are. There's the 159, there's the 129. Here's the 168, there's the 138. Here's the 249, there's the 210-9. All right, so I just simply did regular real numbered, whoops, I went to the wrong place. There we go. Did regular real number distribution. Went to the wrong place. There we go. Regular real number. I distributed over the plus sign, distributed over the plus sign, etc. Okay? Factor out the 10. Okay? Factor out the 10. 10, 10, 10, 10, 10, 10, 10, 10, 10. What's left is this D expansion. There's the 129, the 138, the 219, etc. Factor out the 10. This is 129, 138, 219, 237, 318, 327. So I factored the 10 out of that bottom one. We already recognize this. We recognize this as the left-hand one here. So I intend to show this as 0. Why is it 0? Factor out 10, and you look at 129, 138, 219, 237. Okay, so I factored out 10. I'm ignoring that 10 for the moment. I'm looking at what's left. Okay, so that is the D expansion of this. For example, 129. So when you factor out 10 from 20, you get the 129. There it is, 129. When you factor out 10 from 30, you get 138, etc. You recognize this as the D expansion of something. It's the D expansion of what? It's the D expansion of this. And that involves a repeated row. Where'd that extra row? Well, we did 10 times row, right? We did 10 times row 1 plus row 2. So when we get down to the 10 part, row 1 is repeated. There it is. It's repeated. Well, this has got a repeated row. So its D expansion gives 0. For example, swapping the first 2 rows doesn't change the matrix, but would change its sign. So the same argument that we gave a couple of videos ago shows that the D of this is 0. So the D of this is 0. So this here gives 0 because it's 10 times 0. And so what we have here is the sum of 2 things, one of which is 0. So we're back to the original. All right. So very involved, very involved. At least a lot of real estate takes a lot of space. Okay, and then the last thing I want to do here in this optional section. The determinant of a matrix equals the determinant of transpose, and as happens so often, I'm simply going to do this with an example. So the proof is best done by doing the 3x3 case, and then the n by n case is much the same. So here's the 3x3 case that we've been working with this whole video. There's the permutation expansion for the 3x3 case. Here's the permutation expansion of the transpose. Can you see that that says 2, 1 right there, second row, first entry? And in the transpose it says 1, 2. That's not a mistake. This is the transpose of the matrix I was looking at. Okay. And of course I'm going to compare the products. All right. So let's see. So the ones in the expansion of T are the same as the ones in the expansion of the transpose. So let's pick one at random. How about if I pick this one down here? 2, 1, 3, 2, 1, 3. 2, 1, 3, 2, 1, 3. Let's find it. 2, 1, 3, 3. What was it again here? It was 2, 1, 3, 2, 1, 3. 2, 1, 3, 2, 1, 3. Ah, found it. There it is. Took me a minute. Let's try another one if you're dubious because I bumbled the last one. How about 1, 1, 3, 2, 2, 3. 1, 1, 3, 2, 2, 3. There it is. 1, 1, 3, 2, 2, 3. Okay, so term by term, ignoring the permutation matrices for just 1 second, term by term, I get the same things. Now, that's perfectly sensible because the 6 things up here arise from how do you pick one entry from each row and column, and of course you can pick one entry from each row and column by also picking one entry from each column and row. Okay, so that's perfectly sensible. All right. Now, what about the associated permutation matrices? So each of the permutation matrices is associated in the following way. If, for example, you take the one that has a 1, 2, 2, 3, 3, 1, then that's, of course, associated with the permutation. 1 goes to 2, 2 goes to 3, 3 goes to 1. When you transpose, you get 3, 1, 1, 2, 2, 3, and that's associated with the matrix that takes 1 to 3, 2 to 1, 3 to 2. That is to say, here 1 goes to 2, 2 goes to 1. 2 goes to 3, 3 goes to 2. 3 goes to 1, 1 goes to 3. So these two are inverses of each other. And again, that's perfectly sensible because when you take the matrix transpose, you sort of flip from ij to ji. Okay, but obviously the determinant of P sub phi has got to be the determinant of P sub phi inverse because they're plus and minus 1, and so exercise 16 shows it's easy to see that that the determinant of those two has to be the same. Okay, so these are entry by entry the same. Okay. Okay, and here's just a simple example for 2 by 2 matrices that AD minus BC, and when you take the transpose, you get this, and it's still AD minus CB, even though that doesn't make any difference. Okay, all right, very good. So let's see. Next time we're going to be changing on to the next section, and the next section has the advantage. We'll be back to the check-ins. The next section has the advantage of doing geometry. Geometry is always nice. I like the algebra, but the geometry is always has a sort of a delightful feel. So that'll be fun. Okay, see you then.